Welcome to lesson 1.1, variables. A variable is sometimes thought of as a mathematical John Doe, quote unquote, because you can use it as a placeholder when you want to talk about something, but either one, you imagine that it has one or more values, but you don't know what they are, or two, you want whatever you say about it to be equally true for all elements of a given set. So you don't want to be restricted to considering only a particular concrete value for it. So an example of one where you imagine that a variable has one or more values, but you don't know what they are. So is there a number with the following property? Doubling it and adding 3 gives the same result as squaring it. So it is a very vague word to use. So we are going to use a variable to represent this imaginary number that may or may not have this property. Okay, so we're going to call this thing x. Instead of it, we're going to say x. So is there a number x that has the following property, where doubling x and then adding 3 is the same thing as equals squaring x? Okay, so that is a way of writing that property without using a pronoun. So instead of using it, we're using x. An example of 2 where we want to be as general as possible. We want to say something is true for every element, for all elements in a set, rather than a specific one. So here's the example. No matter what number might be chosen, if it is greater than 2, then its square is greater than 4. So if I wanted to use variables, I want to replace the its with some variable, we'll call it n in this case. So no matter what number might be chosen, so I'll say for any number n, if it is greater than 2, so if instead of it, I'm going to use n is greater than 2, then its square, which we would represent as n squared, is greater than 4. Okay, so now we're going to do a couple more. We're going to use variables to rewrite these sentences more formally. Are there any numbers with the property that the sum of their squares equals the square of their sum? So we're looking for multiple numbers, so we'll say 2 numbers. Is there an A and B such that the sum of their squares, so that means square them and add them, so the sum of their squares equals the square of their sum, so that means add them first and then square them. Okay, so that's just a little fact to ponder. We're not going to answer it right now. We're just working on translating these English sentences to more mathematical notation using variables. And for B, given any real number, its square is non-negative. This is just a statement, and it's always true. Given any real number, if you square it, it is non-negative, meaning 0 or positive. Okay, so there's that vague pronoun. We are going to use a letter. Let's call it x. So given any real number x, its square, which would be x squared, non-negative means bigger than or equal to 0. All right, here are 3 important kinds of mathematical statements. We have a universal statement. That's a statement that says that a certain property is true for all elements in a set. It typically contains some variation of the words for every. So for example, all positive numbers are greater than 0. That's a universal statement about all positive numbers. And all is a variation on for every. For every positive number, it is greater than 0. So all for every. Those are indications of universality. A conditional statement says that if one thing is true, then some other thing also has to be true. I should say thing. Then some other thing also has to be true. It typically contains a version of the words if-then. For example, if 378 is divisible by 18, then 378 is divisible by 6. Okay, so that is a true statement, and you can see the if and the then. That's called a conditional statement. Now, an existential statement says that there is at least one thing for which a given property is true. And it typically contains some variation of the words there exists, or there is. It's existential, the root word is exist. It's the existence of something. So for example, there's my existential phrase, a prime number that is even. Now we can start to combine these 3 different special kinds of statements. Okay, we can have a universal conditional. That is a statement that is both universal and conditional. So for example, for every animal A, so we've got the universal right there. If A is a dog, then A is a mammal. So it has a universal for every and an if-then, which makes it conditional. So an important property of universal conditional statements is that they can be written in lots of different ways. So it's important to be able to tease out the universal and the conditional part. So here's an example. We're just going to rewrite it a bunch of different ways. Fill in the blanks to rewrite the following statement. For every real number x, if x is non-zero, then x squared is positive. So if part A just says if a real number is non-zero, then its square is positive. So we made the existential part of this statement implicit. You don't see a for every. Okay, it's implicit within the if part of the statement. For every real number x, so we said if a real number, so we've made the for every part implicit. All right, now in B, for every non-zero real number x, x squared is positive. Now we've made the universal piece explicit. We wrote for every, but we didn't write if-then. It's implied. Okay, it's implicit in this statement now. If x is a non-zero real number, then x squared is positive. So again, the universal part has been made implicit. We did not write the words for every or for all or all. So it's a conditional statement, and the universality of it about for all real numbers x is implied in the if part. The square of any non-zero real number is positive. It says the same thing as the original statement. And all non-zero real numbers have positive squares. Okay, another combination is the universal existential statement. This is a statement that it's universal because its first part says that a certain property is true for all objects, universal, and it's existential because it'll have a second part that asserts the existence of something. For example, every real number, so we're talking about every real number, all real numbers, that's universal, has an additive inverse. That suggests the existence of an additive inverse. Okay, so we'll do an example, a non-mathematical example. Every pot has a lid. This is a universal existential statement. We're talking about every pot, and we're talking about the existence of a lid. Okay, so we could say all pots have lids. We could say for every pot P, there is a lid for P. Or we could say for every pot P, there is a lid L such that L goes on P. Okay, now we have existential universal statements, the reverse. So we just did universal existential, now we have existential universals. So that is a statement that is existential because its first part asserts that a certain object exists. Okay, so first part is existence. And then the second part is universal because it says that that object satisfies a certain property for all things of a certain kind. For example, there is a positive integer, so there's my existence. There exists a positive integer that is less than or equal to every positive integer. So there's our universality, every positive integer. So there exists a positive integer that is less than or equal to every positive integer. This is a true statement. It's the number 1. 1 is less than or equal to every positive integer. Okay, it's less than or equal to every positive integer. Less than every other integer, and it's equal to itself. So less than or equal to every positive integer. Okay, so we'll do another non-mathematical example here. Fill in the blanks to rewrite the following statement. There is a person in my class who is at least as old as every person in my class. So let's see, some person in my class is at least as old as every person in my class. There is a person P in my class such that P is at least as old as every person in class. There is a person P in my class with the property that for every person Q in my class, P is at least as old as Q. And let's see, what does this actually mean? When you say, I'm at least as old as she is, that means that you are as old or older. At least as old means you are as old or older. So what we're really saying in this convoluted statement is that there is an oldest person in the class. Some of the most important mathematical concepts, such as the definition of a limit, can only be defined using phrases that are universal, existential, and conditional. They'll require us to use all 3 phrases: for every, there exists, and if then. So, for example, this is the definition of a limit, the formal definition of a limit. You may or may not have seen it in a calculus course. It says that if you have a sequence, A1, A2, A3, A4, etc., if you have a sequence of real numbers, if we want to claim that the limit of that sequence, A sub n, as n approaches infinity, is L, if we're claiming that it has some limit L, that means that for every positive real number epsilon, there is an integer capital N, such that for every integer little n, if little n is bigger than capital N, then we can sandwich the difference between the sequence term and the limit between negative epsilon and positive epsilon. Understanding this definition at this moment is not of great importance. I just wanted to show an example where just a definition of something that you've already studied, a limit, when you want to write it out for very precisely and formally, can look very complicated. Okay? You may need all three of these types of phrases in one definition.